Hello, everyone. This is Spencer Snowling from Hatch, and I'm glad that you can join us today for our regular monthly GPS-X webinar. So today we're going to be talking about how to model IFAS and MBBR systems using GPS-X. And so I'll be talking about our biofilm model. I'm going to show you how to model different types of technologies. And as always, I like to be able to run a number of different desktop scenarios that are going to kind of show you a few things as we go along today. So if you have any questions, please type them in the chat box. So what we'll do is, like normal, you can put your questions there, and then we'll collect those up during the presentation, and then I will stick around at the end and answer as many of those questions as we can. So here's the plan for today. We are going to talk a little bit about attached growth media processes. I actually did a little bit of hunting around this week and put together a little bit of history of the development of attached growth processes. And I'm going to talk about different types of IFAS and MBBR technologies and then go right into how our GPS-X biofilm model structure is able to capture the performance of those. So I then will flip over and talk about, as I often do when we're talking about a specific unit process model, going to talk about all the menus, all the settings that you should be aware of, and the ones that are important for you to know about. I'm going to do, as I'm almost always want to do, a little bit of a sensitivity analysis on using the model. So I tried to put together a few small examples that are there that can kind of give us a flavor of what you can do with it for your particular projects. Okay, jumping right in then. Let's talk a little bit about attached growth processes. So just to make sure that everybody's familiar with the terminology, we're talking about processes where we have a surface of some kind, either fixed in the system or floating, to be able to grow concentrated activated sludge biofilm. So the bugs grow right on the surface rather than floating around in the liquid. This process, therefore, then relies on the diffusion of the soluble components that we're dealing with in these systems, oxygen and ammonia and the carbon substrates and so on, diffusion of those into that biofilm so that they can interact with the biomass that is growing on that surface. And the reason why this is a good thing is that it allows for higher than normal concentrations of biomass in the reactors, and also it does provide you with the opportunity to sort of fix some of that population in place. Right. Okay. So I went through a little bit of research and hunting around. I was reading up on sort of the history of activated sludge in general. And really, attached growth processes are not at all a new thing. And in fact, they basically predate the regular suspended growth processes that we find in conventional activated sludge. And I was acquainted with the history of this particular person, Sir Edward Franklin, a British chemist who, while I think he was more famous for other things that he did in his career than stuff with wastewater, he did sort of was one of the first people to very early on study the process of filtration for treatment of waters, and looked at both the sort of physical, chemical, and biological aspects of running water through soil and seeing what happens when you do that. Right. So the work that he did then led others to be able to lead into the idea and the concept of the first attached growth processes, which were trickling filters. So the first trickling filter actually was built in 1895 at Salford in the UK, and the first American or North American one opened the trickling filter operation in Reading, Pennsylvania in 1908. So both of these, of course, predate conventional activated sludge, which didn't arrive until the early 1920s. Now, in all of my Googling around this week, I was really desperate to try and find a picture of either of these two anywhere, or a sketch or drawings or anything, and I sadly couldn't come up with anything, but I did come up with a couple of nice pictures of sort of older style trickling filter operations here. This is very common, one that I've seen in the times that I've traveled through the UK. And these are, often stone structures, and they're often filled, I think originally were filled with a rock media of some kind. And then, you're of course distributing the wastewater on the top there, and it percolates down, and there's a drain through the bottom to collect the treated water. Now, this particular one, you can tell by looking at it, and I apologize, it's not a great resolution here, but you can see that this is actually modern plastic media, these kinds of rings here that are part of this particular process. So not uncommon to find these types of systems still in use throughout North America and quite a bit in Europe still. I know there's sort of a trend away from them, replacing them with conventional activated sludge systems, but nonetheless, this is where biofilm kind of started from, right? And we, of course, have a model in GPS-X, a unit process model for trickling filters. So moving on to more advanced technologies, they came along later in the 1960s and 70s, these rotating biological contactors. These are systems that are often of this sort of corrugated plastic sheets put together in these kind of canisters that then rotate around and dip into the treatment water, so you can grow biofilm on these surface areas. Here's a very, very popular technology. There's a couple of these around here in Ontario and Canada, where I'm from. And we, of course, have models for these in GPS-X. But then later on in the 90s was sort of the beginning of looking at this type of IFAS and MBBR media, right? So extruded plastic with ridges on them and other things to kind of create a lot of surface area. That also became quite popular. And then after that as well, there's also been a development of a variety of other types of biofilm type processes. So BAFs, they're biological aerated filters that combine filtration and aeration and growing biofilm on those processes. We have models for those in GPS-X as well. And then also membrane aerated bioreactor, which is sort of probably the most recent sort of unique technology that has sort of hit our market there. And we have a couple of different forms of that model as well. And I'll just quickly highlight the fact that we actually have webinars on these two technologies that you can come to our YouTube channel and take a look. So if you go and look at what's new in version 8.5, my colleague Nick Piccolo did a nice talk on our newest BAF model. And I gave one a couple of summers ago towards the beginning of the pandemic lockdown time on modeling the MABRs in GPS-X. So feel free to pop over to youtube.com/hydromantis and you can find all of those details there. Let's move on to talking specifically about IFAS and MBBRs. These are mostly what I'm going to talk about for the whole rest of the webinar today. So, of course, it's a very popular technology. And the idea is you have this plastic media, which you can add to existing tanks. These are designed to have a very high specific surface area so that you can get a lot of room for your biomass to grow in a small area or small volume. And somewhat near neutral density. I've heard a couple of different explanations about this over the years, but the idea is, of course, you want to have good mixing. So you want to have the plastic being, roughly equal to the density of the water so that they can exist throughout the whole tank. They don't sink or float. But I have heard that they are designed to just possibly a little bit be lighter so that in the event they need to be removed, they can float up. So the biofilm then grows on that media surface and then remains in the bioreactor while the wastewater flows through. These systems require a certain amount of careful mixing to be able to make sure that, first of all, you get the media itself spread all the way around through the tank and sort of optimize that process so that you can get exposed, first of all, to all of the wastewater coming in. You want to make sure that you've mixed all of that biomass that's on all those surfaces so that it gets interacting with the bulk liquid that contains all the ammonia that you're trying to get rid of, for example. And also, you need some screening to make sure that you keep these little plastic pieces of media, in the place that they're supposed to be in your plant. So you don't want them to float downstream. I've been to a couple of plants where there's been issues that they had stuff escaping. And in fact, even one where all kind of piled up down to one end and it sort of heaved up and over onto the grass and onto the walkways and so on. There are ways to deal with these physical aspects. So I won't be talking about that today, but mostly we're going to just stick to talking about the process stuff. Right, so there are many, many different types of media. So originally I was going to put all the major dealers on here, but I realized when I started on that process that Uh, by the time I looked at all the different technologies out there for these types of floating plastic media, I would have had to have had 5 slides worth of them. So I'm just going to show you a few. The idea that they all kind of work in the same context. You have a large number of these small plastic pieces that are configured in different ways, and you put them in your tank, and then the biofilm will naturally grow on the surfaces of these things. So some of them have, room on the inside to sort of grow the biomass in a protected area. Some of these chip ones are very porous, so you got the idea that biomass kind of grows inside them and gets protected in that kind of way. So I've seen lots of different versions of this, and even systems that use a mixture of different types of media together. There's lots of interesting things that you can find out there. Right. So the amount of surface area that you're going to use is then a function of how many of these pieces you have, and what is their specific surface area? How much surface do they have per piece of media? So that's going to be partly an issue when we come to calibrating our model. So that's some of the information that you will have to provide at that time. Okay, so what I'm going to do then is I'm going to, at this point, sort of talk about the GPS-X biofilm model structure. So this is actually relevant to all of the GPS-X biofilm units, trickling filters and MBBRs and all of the other stuff too. But just to give you an introduction, if you haven't already heard it in one of our past webinars or one of our training sessions. So the idea that we employ in any particular reactor that has media in it is that while we assume that the media itself is, all of these little independent pieces floating around with each other, we take the parameters that you have entered in the model, and then we calculate what is the total amount of surface area that those pieces have. And then we convert that to sort of, or think about it as being one big homogeneous sheet of media. Then the biofilm will grow on that. So by default in GPS-X, we have 5 biofilm layers. There'll be the layer that's closest to the media, and then ones on top of that, 5 of them all together. And then that outermost layer will be in contact with the bulk liquid. Now, in a trickling filter, that would be the liquid that falls kind of, downwards over the system, or in a BAF, it would be the upflow part. In an IFAS and MBBR model, basically that outer biofilm layer is in contact with all of the rest of the liquid that is assumed to be completely mixed outside of that system. So, sorry, outside of that particular reactor that we're in. So basically you have 5 biofilm layers and then the bulk liquid layer. Okay, so I tried my best here to sort of give you a physical representation of what this looks like. So I picked one of the pictures that we had earlier, and I'm going to zoom right in here on this piece of media on this particular little pocket. And so what I described previously is essentially this. If I take that little tiny slice of the plastic media itself, you can see that there would be these 5 biofilm layers standing on it. And so that is how we model it across all of the surface area that is there. Now, this, of course, is making an assumption that the layers themselves are homogeneous, which we know that they are not. Some are going to be thicker and some are thinner and so on. So really, this is an average representation of that and is sort of the standard way of modeling these sorts of things. So then that outermost layer is in contact with the rest of the bulk liquid, which would include, what's in this hole here, and then all the rest of the liquid outside the unit and all the way throughout the whole rest of the tank. So what we're going to be able to do is mass balance modeling, as we do in GPS-X, and of all of the different components of our activated sludge model. So we will get a concentration prediction for the bulk liquid out here for all of the units that we normally are used to having. So, our oxygen, ammonia, nitrate, phosphorus, all that good stuff. And then also a concentration profile for each of these 5 layers as well. So these are actually treated like 5 little individual reactors, and then a 6th one out here, which is the liquid of the whole rest of the tank. So it is a fairly complex model in the sense that, even though it looks like a plug flow tank when you drop it on the drawing board, it's actually 6 times as many mass balances and 6 times as many state variables that we are predicting with our model. So the good news, of course, is that we've got our solvers and everything all trained up and ready to go and to be able to solve all that for you. So So in addition to the biological reactions that are going to happen in every one of these layers and also in the bulk liquid, and by biological reactions, I mean the growth and death and lysis and hydrolysis and all that kind of stuff that happens in a regular CSTR, we are going to have a few other processes on top of that that are specific to biofilm. So the first one is attachment and detachment of solids. So our liquid out here, depending on the way it's been configured at the plant, is going to have at least some solids in it, probably, right? It's coming in the influent a little bit, and we're having some biomass probably growing out here too. So the solids will attach onto this outermost layer, and then of course some of the things are things that are growing in here. So we're going to produce probably a lot of inert material as this biomass dies. So that stuff is going to detach back off again. So now in reality, it's probably a little bit of a sloughing event, but we do it in a continuous kind of way so that you can solve it for steady state. Right. Okay. So that's the particulate part. The soluble part is regular kind of diffusion to and from the bulk liquid. So we're modeling the diffusion of, say, things that are a high concentration out here, but maybe low in here, such as, for example, the oxygen. If we're aerating out here with diffused air and we have a nice, high 5, 6 milligrams per liter, and it's not in here, we're going to diffuse the oxygen into these layers, and also the ammonia and substrate and everything else will be going in there too. And then we have diffusion within the biofilm layers. And we also have internal solids exchange, which works like a little bit like the diffusion in the sense that it's sort of a gradient driven thing. However, it has its own calibration to it as well. So really the important part of this is that, when we're growing the biomass, particularly on the very inside layers, and that biomass eventually dies and produces inerts, eventually they get pushed to the outside and then they will detach off and go out with the regular sludge that we would be producing. So lots of moving parts in a biofilm model. So you can imagine then when we want to implement this in a traditional or a useful wastewater engineering context, what we need to be able to do is to configure this hydraulically in the way that makes sense for the technology that we have. So we do that by basically taking, let me just go back one slide here, basically taking the thing that I showed you before and then just repeating it over and over again in series. And what the representation is sort of the flow moving along the bulk liquid and interacting with the different parts of the biofilm. So for example, in a trickling filter, as I showed you that picture of earlier, the flow would come in at the top, and that flow would be out here in the bulk liquid moving down and then eventually exiting. But in each one of the layers, we would get the prediction of the solids here, and then that would interact with this biofilm. You'd have attachment, detachment, and diffusion and all that stuff, all this biomass growing in here, et cetera. And then that would move to the next layer, same thing. That allows us to sort of model a complex system that is going to have different concentrations as you go down through the vertical sections of your filter, or in the case of IFAS, it's going to be rearranged like this. And this represents the tanks in series, right? So this is the IFAS object in GPS-X, and as you can see, I kind of stretched it out here so it looks like this. It is 4 reactors in series by default, and they have media in them. So these little black dots represent the floating plastic media. So we have media, we have our 5 biofilm layers and our bulk liquid, and then the flow of the wastewater flows through from left to right as it does in this particular object. So that's kind of my best explanation of sort of the hydraulics of how everything come along. And that's how we go about doing that. So really the big action going on here is as this wastewater is going through, getting the components in and out of this biofilm and all the biological activity going on in that biofilm. And the great part of all of this is that you can plot all of this stuff. The biofilm model has basically everything else you'd normally see in a regular activated sludge model, but it's just got 6 times of it. Okay, so let's move on and talk about the IFAS and MBBR unit process model itself. Okay, so first of all, if you go to the attached growth processes here, you'll see actually many of the other objects that I mentioned earlier. And here's the IFAS one. For very, very long time users of GPS-X, we used to at one time call it the hybrid model. hybrid meaning a combination of both suspended growth and attached growth. But we moved to calling it IFAS quite a few releases ago. It's a little bit more accurate since it's set up for that particular context. Okay, so if you open up, or what I would like to do now is actually that thing that I always do when we're talking about unit processes, which is I'm going to show you all of the menus here quickly. I'm going to highlight the parameters that you need to worry about. These are the ones that are important. If there's parameters on these menus that I don't mention, those are because you can just leave them at the default. So I would like to try and just focus everybody's attention and time, since I know you're all busy, on just the most important things that you need to know when you're setting up one of these things. So if we go to the first one, right click on that object, go to input parameters, and then we'll start with the physical menu. This is, of course, where in any of the GPS-X models, you're setting up the details of how, how big this unit is, basically, right? So this part of the top of the menu is exactly the same as a regular plug flow tank. So we're specifying how many units in series do we have, and then also what is the volume of those reactors. So all of the options that you're used to seeing for a plug flow tank will be here as well. Then the next two sections describe the media itself, how much we have and what the characteristics of it. And I'm going to come back and look at these in more detail. And then this one down here at the bottom, I get a lot of questions about it. It's something you don't need to actually change. It's just something that we are doing in the background to sort of enable the models to solve smoothly and run quickly. So you don't have to worry about this. This is just indicating some details about the integration of soluble components. Okay, so for that middle part, this is the important part. You need to specify the reactor fill fraction. So I've heard this referred to with different words, but basically what we're saying is what percentage of the tank is going to be filled up with the media. So if you were standing above an empty tank and looking down and you could just see, they had poured the bags of media in there and you could just see that the top of the media had filled up 50%. That's the kind of thing I mean. By fill fraction, we're talking about, the amount that you would see outside looking at it externally. We do a separate calculation to find out, because all the media has holes in it, how much actual plastic is in there. What we're talking about is I'm just filling it up 50%. That's what we mean by fill fraction here. And then these three parameters here are the ones that are related to the specific type of media that you are using. And one of the main key ones there is specific surface area of the media. And you'll see here, it shows that it's 500 in units of 1/meters. And what that really is, or maybe the more intuitive way to think about it, is it's actually meters squared over meters cubed, which reduces to 1/meters. So meter squared, meaning meter squared of surface area per meter cubed of a bunch of pieces of plastic. And what we're saying there is, like, for 1 cubic meter, we're going to end up having 500 square meters of surface area on all of that. Now, this is a relatively conservative number for what you might get if you were to ask the vendors about it. Partly the reason we do that is that we tend to keep all of the numbers in GPS-X well calibrated and reflective of our experiences of using the model and that of our clients. As you may have noticed on some of those pictures that I showed earlier, you don't necessarily grow biofilm on every single square millimeter of the media itself. They tend to grow more on the inside in all of those holes. In fact, they're designed specifically to work that way, so that the outer parts that bang together against each other, you might knock off some of the biofilm there. So it may say, well, it's 1,000 meters squared per meter cubed, but we want to use a number that's like a little bit less than that, probably. Right. Okay. So whatever number you feel comfortable using here, you might even calibrate this number a little bit depending on what kind of data that you have. But generally, this is a number you should be able to find. Water displacement basically here just tells us that 18% of like if I'm holding a few of those plastic media in my hand, 18% of it will be plastic, and the other 82% will be holes full of air. So that's all we really need. What we're doing with that calculation is figuring out, once we put all of the media into the tank, how much water does that displace? Because then our calculations of all of the rest of the bulk liquid needs to use the correct volume. That's why we have this particular parameter. So anyway, these ones here, density, we just use for just calculations, again, if we're doing some mass balances of across the system. So now these, there are a number of other parameters here that are at the bottom of this tank. These are describing the biofilm itself. And these are the ones that describe how thick it can grow and so on. These are numbers that we have worked quite a bit over the years to keep these up to date with the types of technology that are being used. And generally, you don't have to change them very much. The only one that I would ever need to touch would be the maximum biofilm thickness. And you'll notice, if I click on it here, the default for IFAS is 0.5 millimeter. That means that the biomass on the surface is allowed to grow out to a maximum of 0.5 millimeter, and then any other growth that happens after that internally basically just pushes mass off. It just detaches. The detachment rate goes up the closer that you get to the maximum biofilm thickness. And this works really well. We tried different methods of doing this kind of concept over the years, and the one that we have now works actually quite well. You can calibrate the model itself by making it a little bit thicker or a little bit thinner, but we found like that the technology, floating media in a tank 0.5 millimeter is generally quite good. So there are other units in GPS-X that you'll see that have different default values, like the trickling filter, I think it's 1 millimeter, and in the MBBR, I think it's a lot less. It's like a 0.25 millimeters. So this is a parameter that's there to represent sort of the physical interaction of the pieces moving around or not moving around as need be. So you can adjust this if you like, but I think 0.5 millimeters is a pretty good number. Right, moving on to the operational parameters menu. I won't go into a lot of details here because this is almost exactly the same as you would find in a plug flow tank. So this is really about aerating the system. So you'll find all of the usual stuff specifying the diffused air details. You'll find the ability to use a DO controller here. Our DO set points are a little higher because usually in an IFAS system, you have a higher amount of aeration just to keep everything well mixed. One thing that is a little bit different is if you get down here to the very end of the menu, internal recycle settings. Normally we would have just the left 3 or 4 things in this one. These particular parameters are specific to IFAS. So I just want to take a really brief moment here to discuss those. If you can, what we're doing here is we have a couple of settings that allow for the media to move around in these particular systems. So this one says flow from tank contains media ? And then what that means is we're allowing the media to move from one tank to the next downstream and actually to move around in the internal recycles and so on. So now this would be completely, you would have to, of course, be using an appropriate type of media that can survive being pumped. Or use appropriate types of pumps that will allow the media to not get destroyed as it went through the pumps. As you can imagine, it's not a very commonly used approach for media, although I have heard of it in certain projects in the past. I have to say I've not actually modeled many plants that have this, but anyway, it's an option that we've always had in GPS-X way back since the 90s when we first put this model in. So this one allows, basically you just say, yes, the media travels out of the tank, or no, it doesn't. So by default, we've got no turned on here. But let's say, for example, you had something like this where there was media here and you were just doing this internal recycle. Well, then these 3 units would probably end up with more media than this one. So, and then we also have the ability to do this as well. This is called the concentration factor. And this would represent actually the media going into the clarifier or other places where it would get concentrated and then brought back in with the recycle. And so we don't actually model the actual media moving outside of the IFAS unit, but what we do is we bring it back into the internal recycle or the RAS, and then we do a mass balance based on the number you've entered here. So if you entered in 2, it would say it's going to come back at twice as concentrated as it was when it went out. So what we end up doing in this place is actually we end up integrating the actual surface area as the things move around. And if something changes, then, the biomass that was grown on those particular units would also be accounted for as it moved from unit to unit. So anyway, it's there for you if you need to use it. Please let us know if you have any questions about that. Okay, moving on to the third menu, mass transport. This is the last one I'm going to talk about. All the rest of these other menus are exactly the same as you would find in any other unit in GPS-X. Mass transport is a menu that is specific to all of our biofilm units, and it is basically attachment rate, detachment rate, and shear factors, and external solids exchange rate. They're essentially the parameters that go with all of those processes that I mentioned on that slide before about attachment, detachment, and so on. The only thing, and what I'm going to say is I recommend not bothering changing any of these. We've worked out really good values for all of these over the years. Unless you have a very unusual biofilm, these numbers will work for you quite well. So the only thing that might be something you might want to touch on is actually in this More button right here. If you click on that, what you get is a very long menu with the diffusion coefficients for all of the different soluble state variables in the model. So oxygen's here at the top, but you also have it for the substrate and the various other things that are here as well. So you can feel free to make changes to these if you want to use that to get slightly better penetration of oxygen than maybe what the model is showing you. You can calculate those things, and many of these numbers here are taken from standard textbooks, but we've adjusted and calibrated a few of these numbers from our various projects. So you'll note, for example, here the readily biodegradable substrate, this sort of bigger, more complex carbon molecule, has a lower diffusion constant than something small like oxygen or what have you. Okay, so now that's all I had to say about the inputs. Now I want to talk a little bit about the outputs. Now, because this is a somewhat more complex model and it actually produces a huge amount of information, you can look at concentrations in many, many different ways. And so we have a very large number of menus on our biofilm objects. And so what I want to do is a run through of what we have. And then hopefully you can use this as a reference from our YouTube page in the future to make sure that if you're looking for a particular thing, you'll know which one of these menu items to get to work through. All right, so basically the main ones that you're going to want to touch on are these biofilm profiles menus. And so what this is looking at the penetration or the concentrations as we go into the biofilm. So here we can see, for example, this is the DO profile. And what we're going to see is that on the left is hang on, I've lost my. On the left is the bulk liquid. So this is the concentration out in the bulk liquid. And then here's our 5 biofilm layers. So the innermost one is the biofilm layer that is up against the medium. So when you drag this from this menu into the outputs tab in your GPS-X simulation panel, you will see that it automatically makes this and it orients all this information in this way. Bulk liquid on the left. This is the interface between the bulk liquid and the first biofilm layer, and then the inner biofilm layers are over here. Right, okay, so that allows you to sort of plot, and I will note that this is a very long menu because there's one of these profiles that you can drag onto a bar graph for every component. So, oxygen, ammonia, nitrite, nitrate, and all the phosphorus and all the substrates and everything, all of that stuff. So that's one top of the menu. And then it repeats again and again and again for each individual reactor in series. So it is probably the longest menus in GPS-X are here. So you can dig through, find what you want. If I want to see the DO profiles and all of the different tanks, you can dig through and plot them all separately. But just a spoiler alert, I'm going to show you in a minute, there's an even better way to do it. All right, so displaying the concentrations now in the reactor. So this is now not anything in the biofilm. This is only looking at the bulk liquid as it passes through the length. So before we were looking into the biofilm, now we were looking along the length of the bulk liquid. This is called concentrations in reactors. It's essentially the same meaning as when you have a plug flow tank and you go to that same menu in the plug flow tank and you plot the concentrations as it goes down through the plug flow reactors. So in this case, it's only looking at the bulk. So basically upstream is on the left when it enters that tank, and then downstream is on the right. Okay, so but we can do two of those things together at the same time. And that's what these graphs are. These are found on the 2D concentration variables menu. Now, I know these look complicated, and and often even myself, I have to sort of remind myself which way it's oriented. But these are very, very useful things that you would find where you can, instead of plotting many, many, many graphs, we've condensed them all down to one thing here. So the way this looks is that, first of all, the reactors are on this axis and the biofilm layers are on this axis. So basically, there's the very first graph I showed you, the blue with the oxygen on it. That would be one of these things going backwards here. So starting at the front and going to the back was what I showed you before. So what we've done is we've stacked them side by side for all of the reactors in series. So up at the front, in the front row, is the concentrations in the bulk liquid. So then you have this second row is essentially your outermost biofilm layer, the one that's in concentration with the liquid. And then at the back of this graph is the part that's up against the media. So now this is really useful. I really like this way of looking at things because it kind of condenses a lot of information into one particular graph. So for example, what are we seeing here? What is the story that is being told to us here? Right now, we can see in the bulk liquid up at the front here, that the dissolved oxygen is exactly 4 milligrams per liter all the way down. And the reason for that is that in this example that I calculated, I had the DO controller on and I had it set to 4 milligrams per liter in all 4 reactors. So that's why the airflow has been adjusted to hit there. Then there's a bunch of oxygen diffusing into the layers here. So if you were to look in behind here, you can see that it's quite anoxic on the inside in the first reactor, meaning, of course, that there's a huge amount of biological activity happening right up front where all the substrate and all the ammonia and everything is. So as per usual, you expect more biological activity at the front of the tank. So, and we're diffusion limited on oxygen here is what this is telling us. Less so in the second reactor and third and fourth and so on. So we can see that it catches up with the rest of the load by the time you get to the end, such that actually we get pretty much full penetration of oxygen here. It's 3.5 or something at the back here, even though it was like close to 0 in the first tank. So lots of information. I find a really useful way to deal with this. And this is available not only for IFAS, but all of our units, including MBBR, where in fact this ends up being the other way around. You find the high concentrations of oxygen at the back instead of at the front. Okay, so that was a whole lot of talking, and now I want to get on to doing something more interesting. Let's look at a desktop demo. And so I'm just going to run through 3 very quick demonstrations of using the model in different ways. And that way it'll hopefully sort of give you a few thoughts about how you might want to employ that with your projects. Okay, so first of all, I'll mention that this layout that I'm using right now is actually available in the sample layouts menu. So if you're new to GPS-X, I encourage you to investigate this aspect here. So when you install GPS-X, it comes with about, I believe, 100 or so now unit process models that have already been put together for you. So go to sample layouts, and we have all these nicely organized here, different kinds of plants. You can see all the different BioP plants and everything organized here. So under unit process examples, the very first one is MBBR and IFAS. So now I've modified this one just a little bit for our example here today. So typical type of plant, you can see we've got primary clarifier, we've got some carbon dosage if we felt like we wanted to use that, secondary clarifier, and then all the sludge is taken down here to the solids handling unit. So I'm going to run over here. Now I got ready to go, and I'm just going to solve it for steady state. So I just wanted to talk a little bit about some of the things that you can investigate when using it like this. So first of all, we'll take a look at the effluent. That's actually what I got in this table right here. Effluent solids are less than 10, ammonia is less than 0.1, and so on. So we're actually nitrate and nitrite is actually at 6. So we're doing actually quite well for our night D-night in this particular example. So right now I'm running this setup, and if I look actually at this tab, which is for the MBBR unit, I'm sure you're familiar with looking at, these various tables and things that are specific to the unit itself. If I slide down this little panel here, you can see we've included some biofilm stuff in here. This is total amount of surface area that's available in that unit. Right here, this is the important thing I wanted to note, is that you'll see that this mixed liquor is actually really small. It's like 100. So basically what this tells us is that this is an MBBR configuration, meaning there's not mixed liquor in the tank along with the media, right? So, and the reason for that is if I double click on the clarifier, I can see that this RAS rate is set to 0 in the setup that I have right now. So that's a way that you would model an MBBR system. It's flow through. There's no recycling of concentrated sludge. And I can go in here and I can plot some of these 2D concentrations. So here's that one that I showed you earlier. It's actually a screenshot of this exact thing that I put on the slide. So we can see here. You'll note, by the way, that we've got these little buttons here. You can rotate things around just to be able to peek over the edge if you need to. I also find it really quite interesting. I usually put DO and then the nitrogen species so we can see how ammonia is being removed here. I also sometimes will put the biomass concentrations here. So here you can see that all the heterotrophs are living up front here. They grow fast. They're getting growing in the largest concentrations, not in the bulk liquid here, but right up on that first biofilm layer. And then if I look at the AOBs, for example, they're actually a little bit behind in concentrate. Now, this is a much lower axis here. Of course, you always grow a lot more heterotrophs than AOBs, so I had to adjust the axis so you could see this. But nonetheless, you can see they kind of tend to grow a little bit more in the back than they do the heterotrophs do. So it's kind of an interesting thing to look at if you want to see about distribution, especially if you're doing interesting things with internal recycles or what have you. Okay, so there's that, and there's just large numbers that you could look at, like the alkalinity as it goes through the biofilm. You can look at any other number of things that might help you with sort of understanding the process and understanding how things change as it goes through the reactors in series. Okay, so that was for MBBR. I made a scenario here with IFAS. So basically I just turned on that recycle. And I'm going to run that again. And okay, so what this is going to tell us is if we go back here, basically I only put on the RAS recycle at 1Q, and I left everything else exactly the same. So right now we're actually containing a lot more solids, right? It was 8 or something before, now it's 12. And that is because we now actually have a mixed liquor of 3,000. Or a little bit greater, along with all of our biomass as well. And we can go back and look at how that's changed things. We actually have less of a gradient here of our heterotrophs. One of the interesting things that you can do is actually look at the distribution of the solids in the biofilm versus in the bulk liquid. And that's actually on a menu. If you right click here at the exit from this tank, and you go to mass, this is something that's available in any one of our bioreactors, the sludge mass menu. For this particular unit, because we have both biofilm and suspended growth, we've actually calculated what is the suspended mass of solids versus the fixed film mass of solids. And here you can see we have quite, a bit of a distribution, maybe 15 or 20% of it is in the suspended form, most of it is in the fixed film form. Now, in the previous one, I sort of showed you there before, this was an extremely small number. It was like less than 1% because most of it was in the biofilm because we weren't recycling any mixed liquor. So, something you can take a look at around that idea. Now, I'm bringing this up partly for one thing that I should mention, which is the fact that we use this mass number here when you do an SRT calculation in GPS-X. So what is an SRT? An SRT of an MBBR IFAS system is a bit of a question of interpretation unto itself. It doesn't have quite the same meaning when you just do a simple mass over mass flow type of calculation that you would have when you just do regular activated sludge. Now, if you were to do it in GPS-X, you'd probably come up, because it's using this really large number, you'd probably come up with something like, oh, the SRT is like 167 days or something. That's because it's counting all of the biomass in all of the biofilm and everything. So just to keep that in mind, that's why that number will come out in a big way. Now, you could argue that is actually the correct way to calculate it. I know other people who feel no, it should only be the bulk liquid side. Well, then you can use those numbers to calculate what you want to do there as well. So just like an SBR and many other things, calculating what the SRT becomes a little bit of a question of the philosophical interpretation. What does it mean that when you're including the biofilm, those units that are the biomass that grows and then it dies inside the biofilm and produces inerts, and then that goes out in the sludge. It doesn't have quite the same meaning as it does in a conventional activated sludge system. Okay, so anyway, that's something that you can use now, just a very simple sensitivity analysis, and you can dig through and look at a lot of interesting details. Okay, I want to do, as I almost always do in these webinars, a sensitivity analysis. So I've created another different layout for that one. And this is basically a simplification of the one that I did previously. Two simplifications that I have made is that this is now just one tank in series. So imagine it's a big CSTR with media in it. Also, I made the influent a little bit stronger, and I also made the tank a little bit smaller. I tried to make it a little more challenging so that we could have some interesting results to talk about. Okay, so we've got that, and what I'm going to do is use the GPS-X analyzer function and do a sensitivity analysis on the reactor portion that is filled by media. So in other words, we're going to run it with different amounts of media in the system. And what I'm going to do is I'm going to start out by doing that in the MBBR format first, even though you can see this connection here, I've got it set to 0. And so we go up to here, we set it to analyze mode. We're going to run it from 30% to 70% fill fractions, and then we'll see what that does to our effluent. So now, not surprisingly, if we just look at COD and ammonia, both of those things go down as you go to more media. And you can see here that actually the nitrite and nitrate actually goes up as you go in this direction here. So we're getting a bit more nitrification as that's happening. I suspect over here, when we were looking previously at those sort of anoxic portion of the biofilm, that maybe there was some denitrification going on in the back of the biofilm there. Sometimes we see that with these systems, and also, of course, many systems are designed to do that very specifically. So that's an interesting aspect here. And of course, there's very little change in the effluent solids because we're not, really dealing with a conventional activated sludge. So we don't have to worry so much about overloading our clarifiers with mixed liquor. Right. Okay, so let's rerun that in an IFAS context and see how that looks different. Okay, so we're just going to let that one run again, and we'll see that for the system with the recycle, that there isn't a lot of difference, because pretty much even with 30%, it was already doing full nitrification. And so this is, not changing a fair bit over time. I mean, it goes down a little bit as you go from right to left, but nonetheless, it kind of does not allow for that denitrification in this particular setup. And again, if we go back and look at those balance of solids here, so I go back to that mass menu, we're looking at, pretty much 80, 13%. Oh, this is almost exactly 10,000. 13%, of our biomass is existing in the mixed liquor. The rest is in the fixed film. However, I suspect that what's going on in this case, in this fully aerated system, is that the biomass that's in the mixed liquor is doing a lot of the heavy lifting here, I'm sure. So, but without that anoxic zone, we're not getting much denitrification. Now, we could put a whole lot of graphs up here and, dig through the details of those 2D graphs to find out exactly what's going on with all of those things. And, if we had a webinar that was 3 hours long, I probably would go through all of that with you as well. Okay, last one I want to do so that I can stay on time here is to look at a dynamic run. So what I did was I made a little layout here that has two side-by-side plants that we're going to compare to each other. So looking at the top one, this is the one with the IFAS, so I definitely have a recycle going here. I have taken the influent that we had from the previous examples. I added a storm runoff to it. So we're going to have a storm on the second day of the simulation, and we're going to run it out for 5 days, and we're going to see how the effluent changes when that storm passes. And then I've done that exact same thing. I just copied this and I swapped it out with one that doesn't have any media, basically a no media plug flow tank. Now, I did sort of set this one up to operate a little bit more like you would do for a regular plug flow tank. So a little, we didn't go to the crazy high aeration levels and so on. And I set an appropriate mixed liquor concentration here. So we can see here now, if you haven't used the storm runoff model before, it's one that we've had for quite a while. And so you can see here, basically, you feed this thing rainfall in terms of millimeters per hour, and then you specify a catchment area, and then it provides you with clean water that kind of runs off over a period of time and eventually peters out to zero again. So I'm running the same storm through both sides of this example. Right. Okay. So first thing is I'm going to just show you what the flow looks like when we run this. And so the influent, I'm keeping the same. I'm showing you just the IFAS side of this right at the moment. All right, come on, there we go. So you can see here in red, this is the regular influent flow, and then here's our storm starting. You can see up here, I'm reading in 2 millimeters per hour of rain for a day and a half, and we get some sort of like a peaking factor of, I don't know, 3.5 or something here. So basically, this is now just all the runoff off of that watershed, and this will continue to come down. So those two flows are then combined and they go into our system here. And then now these two graphs that I have are a comparison of the effluent quality from each of these two things that are receiving, identical influence. And so we can see here, red is the one that is the regular plug flow tank with no media, and blue is the one that is the IFAS system. And you can see that it does have an effect. And it shows here that you get a little bit, protected by having some of that media and having at least some of your biomass growing on the media, because the media doesn't get washed out. It stays in the tank. And so you can see it recovers more quickly from the system, partly because I made it a pretty significant storm. And you can see here that the TSS for the side that does not have the media, for the plug flow side, we're washing out a fair bit of the solids, and the biomass gets washed out a little bit. Whereas on the IFAS side, we didn't actually have to have as much mixed liquor. We could operate it under a lot of the heavy lifting being done by the stuff that was on the media itself. Okay, so of course, how that would pan out for your plant and your situation would be totally a function of the storm and the size of your tanks and how you operate the plant and so on. But just to try and show you that, it might be a different story for you, but this is how you would set that up and do that kind of an analysis. Right. Okay, so that is the end of the 3 examples that I wanted to run. I just have a couple more slides, and then I will be able to answer any questions that you have. So feel free to put those in the chat right now, and I'll get to those in a moment. So I did want to mention that the IFAS and MBBR unit process can be used actually for a couple of other technologies other than just floating plastic media. This is actually stationary media, and I know that, again, there's like a large number of companies that make lots of variations on this concept, but I've done 2 here that I know that can be modeled exactly with the models that we have right now. These kind of cords like this Bishop Waters BioCord, and also these kind of fabric ones too. Like this WaveTech. So basically it's the same model, same approach, same details. All you're really doing in this case is changing the specific surface area so that you can get the right amount of surface area. That's really the key to using these models, is no matter what parameters you enter, as long as once we multiply them all out and we get the right amount of surface area for these things all added up, then we're good to go. Okay, a few final thoughts. It's basically this IFAS and MBBR unit in GPS-X is really quite flexible in a way that you can do a lot of different things with it. It's a quite robust model. We've put a lot of work into it over the past years. We have updated quite a bit around the idea of how the detachment works and making sure it solves nicely for steady state and so on. And that ability to simulate moving media as it moves from one tank to another if you need that. And what I'm often seeing people use it for is, process optimization or analysis and doing things like I showed in these demos. How much media do we need? How much should the fill fraction be? And how does that compare to doing something without media? That kind of thing. And as you saw, lots of long menus. There's lots and lots of parameters, lots and lots of output to play with. But really on the input side, there's really only a handful of things that you need to change. The details about the specific surface area and the displacement and the fill fraction. Those are the sort of the main key things. You may want to touch on the maximum biofilm thickness if you feel that you're really growing a huge amount of biomass on there, more so than would be normally had. Okay, so if you have any other questions about that, please feel free to email our regular support lines and we'll be able to answer any questions you have about how our biofilm models work.